Good morning, good afternoon, good evening, everyone, wherever you're joining us from. Thank you for attending today's webinar on the future of resource recovery. My name is Ryan Andalib. I'm the Marketing Director for Stantec's Water Group in North America. I'll be your moderator today. A little bit of housekeeping before we get started. We'll have approximately 45 minutes of presentation with 15 minutes left for Q&A. You'll be muted during the presentation, but feel free to use the GoToWebinar questions functionality to ask your questions as the presenters are speaking. I will read those at the end, and then I'll also open up your mic, and you'll be able to ask a question live or comment with about 5 minutes left in the presentation if you prefer to do that that way versus that chat mechanism. We'll also follow up with a certificate of attendance so that you can submit your local registering agency to try to qualify for PDH credits. That usually takes me a couple weeks to get to, so just hang tight on those, I suppose. And with that, I'll turn it over to Drew, and he will get us started.
Thanks, Ryan. You can see my screen and the audio's good?
You look good and you sound good, my friend.
All right, thank you very much. All right, well, thanks so much, Ryan. I appreciate the introduction there. I'm Dru Whitlock. I'm the Global Practice Leader for Stantec for the Renewable Organic Solutions sector. And today's presentation will be the future of resource recovery, a blueprint to becoming energy neutral and environmentally and economically sustainable. I'll be presenting the first half of the presentation here, and the slides I'll be going through here, or excuse me, the topics I'll be covering include advanced let me get in the right slide here, advanced biosolids treatment options, and then integrated organics management and biogas utilization and incentives market. So I want to start off with just some common objectives that we're seeing throughout our work on master planning and facility planning with utilities in North America and globally. One of those coincides with the topic of today's presentation that includes really maximizing resource recovery. And within the context of maximizing resource recovery, achieving Class A options and looking for diversified biosolids end use options for sustainability. Many of these utilities that you all operate are decades old at this point. There have been regulatory changes, there have been capacity constraints, so many modifications have happened over the decades, and therefore there are space constraints, and that's a common issue at these facilities. So trying to find space for new assets is typically challenging. There's always the objective of ensuring that the end use, the effluent is achieving, the plant is achieving effluent compliance, and ensuring that there's an understanding of what the solid stream, how the solid stream is impacting the liquid stream. And within the context of that, oftentimes we're looking at side stream treatment options to mitigate those impacts and ensure that effluent limits are complied with and the system is as efficient as possible. Within the objective of achieving sustainability, decision-making processes are becoming more complex using systems like the triple bottom line, where the economic objectives are balanced with the environmental and social objectives. And then, as we'll get into a little bit later in the presentation, there is a very strong trend right now. Some of that's regulatory driven, some of it's driven by the values and needs of specific areas and urban areas in particular. But integrating organics, all organics, including the organic fraction of municipal solid waste like food waste, high strength industrial waste, fats, oils, and greases, and so forth, and co-processing those with the wastewater residuals. And in addition to that, looking at the green waste that can be combined downstream for bulking agent and so forth for maximizing recovery of all organics. About 12 years ago, I was involved in a water research foundation study called O5CTS3 for waste solids reduction. And at that time, as you might recall, there was a really healthy market in pretreatment technologies looking at ways of ensuring that we can minimize the waste activated sludge and overall sludge volume by hydrolyzing material upstream. In that competitive market, many of those technologies have survived, and some of them have waned a bit. What's really come to surface over the last few years in those pretreatment technologies is thermal hydrolysis technologies and thermochemical hydrolysis technologies like thermal alkaline treatment. All of the advanced anaerobic digestion technologies we're still seeing in play for various drivers, including thermophilic digestion, biological hydrolysis, or acid gas phase digestion, post-aerobic digestion, and a lot of interest that I'll get into a little bit more here later on high solids anaerobic digestion, that is intensification processes. Also looking at combination processes like combining anaerobic digestion with thermal drying, composting, thermal alkaline treatment downstream has become popular as well. We're seeing still incineration processes and also those now being combined with anaerobic digestion. Post-thermal hydrolysis is something that Cambia is working on now, and emerging technologies like pyrolysis and gasification. What you see here is a conventional Class B mesophilic anaerobic digestion system with primary sludge and WAS being thickened prior to anaerobic digestion. The biogas is used in a combined heat and power system and final dewatering downstream. And then that can be combined with additional co-feedstocks like fats, oils and greases, food waste, and industrial waste. When we look at adding processes like thermal hydrolysis, if you look at the center of the process flow diagram, you'll see the thermal hydrolysis system in there. But when you look kind of back and forth between the previous flow diagram and this diagram, when you add thermal hydrolysis, it requires the thermal hydrolysis step, but it requires a lot more than just thermal hydrolysis. Typically, a screening system is put in that's a 6mm screen or smaller to get the debris and so forth out of the sludge. A pre-dewatering step is required to get the sludge somewhere between 15 and 18% into the thermal hydrolysis to optimize the heat balance within that system. Downstream of the thermal hydrolysis process, dilution water is added to ensure that the TKN entering the digester is at an appropriate concentration to control the amount of ammonia in the digester itself. There's a cooling step that is required, typically somewhere around 100 degrees Fahrenheit needs to be dropped from the system even after the dilution water is added. The biogas can be used in a number of different ways, but if it's a combined heat and power system, the heat recovered off that needs to be converted to steam through a heat recovery steam generator to provide the heat to the thermal hydrolysis system itself. And that could require some supplemental fuel depending on the type of CHP system you have and the overall heat demand there. Downstream of anaerobic digestion, there's typically a belt filter press dewatering system. This approach has shown to be very, very effective. It can be to Class A if all the sludge is thermally hydrolyzed. It maximizes the kinetics so we can minimize the digestion volume downstream. The rate of biogas production is increased. The dewatering performance is significantly improved from this. We usually get somewhere around 28 to 30% dry solids from these type of systems, and the quality of the cake is very high. It is low odor and a very friable product coming out from that. So it's a great process, but there's a lot going on with it. To take a kind of an intermediate step towards thermal hydrolysis, many facilities are simply looking at maintaining a Class B approach to biosolids management, but getting more out of the digestion system through intensification through high solids anaerobic digestion processes. So that is to take the solids typically from 3 to 4% feed concentration up to 6 to 8%. That can be done quite easily upstream, but sometimes you could run into a viscosity issue of getting that sludge into the digestion system itself. So chemical addition can be used to manage that. As I mentioned before, the alkalinity that's used in some of these processes does a very nice job of reducing the viscosity and potentially providing a little bit of hydrolyzing element to the process upstream. So that's one way to manage that viscosity. Another way is through recuperative thickening, where you're essentially decoupling the solids retention time from the hydraulic retention time, recovering some of that digested solids, sending it back through a thickening process, typically centrifuges, and that back into the digester so that you retain the solids. One nice aspect of this is you get a bit of a TKN ammonia purge out of that, so you can maintain a lower concentration of TKN within the digestion system to avoid any toxicity in there or inhibition. This is a process flow diagram of Kenosha, Wisconsin that has a number of combination processes and has been successfully operating for a number of years now. It includes a thermal alkaline treatment process on the waste activated sludge upstream of the digestion process, conventional digestion in the middle, and then thermal drying downstream. What's interesting about this is that the biogas goes to a combined heat and power system, and then the waste heat is recovered and used in the indirect drying system downstream to provide additional sustainability elements. So it's nice example of combination processes. Another project that I was involved in several years ago is Green Bay, Wisconsin R2E2 process that includes anaerobic digestion, partial thermal drying, and fluidized incineration. In this process, it's a heavy co-digestion system where imported industrial organic waste is combined with primary sludge, and thickened waste activated sludge goes to the anaerobic digestion system, then into dewatering system. From the anaerobic digestion system, biogas goes to CHP for heat and power production, and then the dewatered solids go to thermal dryer. The thermal dryer recovers heat and supplies heat to a pre-drying system to achieve a autogenous combustion in the fluidized bed incinerator. And really innovative process. I'm impressed with that client and what they've done there. This is a image of that facility. I was in charge of the pre-design of the anaerobic digesters you see on the right, and these are really state-of-the-art anaerobic digestion systems. They're silo-shaped units, a very high height to diameter ratio with a cone-shaped bottom, optimized for energy demand as well as energy production, and can keep these in service for a long period of time based on the shape to keep grit out of them and keep them in service. In the center part of the diagram, you'll see the fluidized incineration system and the solids handling system itself. Switching over to integrated organics management, as I said, that there is a very strong trend in this. Some of it's regulatory driven, where, for example, in the state of California, for landfill diversion requirements, we're seeing a lot of co-digestion work there going on in urban areas where landfill costs are becoming high, and the goals for renewable energy production as well as greenhouse gas reduction. We're seeing a lot more interest in integrated organics management as well. And it's really it's the next step into the future of resource recovery as far as I'm concerned for facilities and municipalities, agencies, districts that are looking to continue to improve on their resource recovery aspects. Of course, this refinery in the middle is producing products at the end that include biosolids, nutrient recovery for fertilizer, energy production for vehicle and power production, as well as water recovery. I got several images here of these systems, and now what we're seeing is the evolution now is that these pre-treatment systems for food waste pre-treatment are happening at material recovery facilities, really separate from the treatment facility. And this is one example of, I'd say, a 1.0 version of a separation magnetic metal removal system and screening system at the Central Marin Sanitation Agency. It's just down the street from the treatment facility, so all the pre-processing of the material happens at this facility, and then it's transferred just down the street and injected into the anaerobic digestion system there. This is another good example of LA County Sand District in California. They have worked with third-party providers, but this particular system is something that LA County owns and operates themselves. It's a screening system that has a series of finer screens, sequential finer screens that create this bioslurry that's you see over on the right. The screening system is on the image on the left, and then there's storage tanks on the left that from the storage tanks, the bioslurry is pumped into tanker trucks, and from the tanker trucks, that's transferred over to the treatment facility where it's co-digested with wastewater residuals. The city of Edmonton has really been out ahead of this for a long period of time, and Stantec has had the pleasure of working with them on many projects, including one that just recently we're the owner's agent on a wet digestion system, as they call it, which is essentially includes a conventional digester as the wastewater market would see it, but it's for food waste or separated organic food waste that will be anaerobically digested. The biogas is planned to be used in a renewable natural gas system there, and residuals will be dewatered and reused in various aspects there. It's a very nice system, and this shows images of their existing system there with dry anaerobic digestion system, combined heat and power, and the biogas storage and percolate recovery system on the lower left portion there. Another good example is Stantec is currently, through the program management services, is examining a fully integrated organic system for Atlanta Metro. This is a good example of what's happening in a lot of these urban areas where their landfill capacity is limited, prices are going up, and there's a desire to do something beneficial with the residuals. So the city, led by the city of Atlanta themselves, and these accompanying counties and agencies associated with them, are looking at a regional facility that will co-process wastewater residuals with recovered organics from the municipal solid waste, as well as high-strength waste and fats, oils, and greases. Because of the magnitude of this facility, there are a number of different treatment options. In the center portion there, we're looking at modifying one of the facilities to include a thermal hydrolysis system. This is really where the energy is going to be produced through thermal hydrolysis, anaerobic digestion, combined heat and power, and there'll be a solar project associated with this as well. So a lot of energy being produced at that particular facility. Organics are planned to be recovered and transferred to a regional organics to soil center, where there'll be some composting of Class B material to upgrade that to Class A and have a diversified product. The one thing that's very nice about this is that because of the diversification of the feedstock, as well as the treatment processes and the end products, it really provides a lot of flexibility to the management staff ultimately of what they can do with it. So we'll have a whole bunch of different types of feedstocks coming in. Management staff will choose where that goes and where it can be optimized in anaerobic digestion, a drying system, and a composting system, and optimize that to meet the market demands on the back end of that with a thermally dry product, a hydrolyzed anaerobically digested product, and then a composted product at the end of that. And those can be used independently or blended, and just a lot of flexibility there with that particular system. Okay, last bit here is just on the biogas incentive market. We're seeing a lot of activity in the biogas incentive market now, and just want to give you a quick overview of that. For these incentive programs, biogas can come from wastewater facilities or publicly owned treatment works. They can come from private commercial entities that include dairy and food and beverage companies, and also biogas from solid waste. Of course, that biogas can be upgraded to produce power and heat through a combined heat and power system. And also the CO2 can be removed so that it meets a natural gas grade quality, and that can be used for various demands. For the incentive programs, though, in order to realize many of these credits, the fuel has to go to vehicles. So it either needs to go to an electric vehicle on the one hand, or it needs to go to a compressed natural gas vehicle on the other hand. So we are seeing these the RIN programs through the Renewable Fuel Standard, as well as the California Low Carbon Fuel Standard, incentivizing this. Based on the current incentive market, when you add up all of these incentives together, as well as the wholesale value of natural gas to go to a natural gas vehicle, the incentives are quite high. We're estimating that if you're able to get all of that and get a takeoff in California, you're able to realize up to $40 per million BTU, which is very, very attractive, and the payback periods are quite short for those programs. So there is a lot of activity there. The challenge for some of these public entities with a fiduciary responsibility to their ratepayers is it comes down to really the risks and uncertainties around the market, and if the incentives are going to be sustained, or if they're going to change significantly to change the economics, and that becomes a bit of a challenge. So we have been working with many of our clients on really educating them on those programs and running risk analyses to determine how they want to go forward and the best use of that gas. With that, I'm going to transfer it over to my friend Mehran, and I'll be happy to take questions at the end of the presentation.
Thank you. Thank you, Drew. I'm wondering if you guys can see my screen.
We could there, Mehran. We just lost it. Now we're seeing your Outlook.
Can you see it now?
Nope, we're seeing your Outlook now.
Okay, Outlook. Oh, sorry.
There you go, and hit that presentation mode button. There you go, sir.
Perfect.
Thanks.
Thank you very much, Drew. Before I start, I'd like to thank my colleague, Dr. Yuan Fang, who did a lot of work on some of these slides here today. In this presentation, I will share with you a simulation practice we conducted to measure the degree of energy conservation attainable at one of the largest plant in category, which is Bonnie Brook. Drew went through a lot of technologies in terms of the energy production and conservation, but in this case, I'm gonna really talk on the specific case and see how really attainable that is in your own specific plants. So we know that in general, a wastewater treatment plant is a very energy intensive process. We have to spend a lot of energy there. In addition to that, if you look at a plant from a circular economy perspective, wastewater and water treatment can consume a lot of electricity off the grid. In the U.S., it's reported up to 4% of total electrical power produced in the U.S. is consumed by water and wastewater. In different countries, that number may change. In Europe, that is reported lower, between 1 to 3%, but it's still, that's a significant amount of energy. So it's very essential to be cognizant about the plant energy consumption and how we can really push a plant toward more energy conservation, energy neutrality, and even in some cases, energy positive. The left graph here shows plant energy consumption in 18 treatment plants that I put together. That's an average between those 18 treatment plants that shows over 53% of the energy in a plant is consumed by the aeration, around 17% by sludge treatment, and the rest with pumpings and others, buildings and so on, heating system and so on. We see that the majority of the energy consumption in a plant is actually through the secondary treatment and the sludge treatment. If we look at the aeration itself, we know that the energy efficiency of aeration is a big function of the technology we use, the equipment we use. However, operation of a plant can have a significant amount on the energy usage in the aeration side. The right graph here shows how the kilogram oxygen consumed per kilogram BOD removed in a secondary treatment, as a matter of fact, can be a big function of the F2M, which is food to microorganisms ratio, as a very important factor in the operation of the system. So in addition to technologies, it's very important to operate a plant at optimum condition in order to move toward energy conservation and neutrality. In general, the specific energy consumption in a plant average between a lot of plants around 0.46 kilowatt hour per cubic meter. That number can go as high as even 1.5 kilowatt hour per cubic meter. One of the questions that I will have for the plant, maybe we can talk in the discussion, is how much you guys use in your plant. So this figure shows the Sankey diagram of various sources of energy entering a typical medium to large size wastewater treatment plant, which consists of a primary clarification, biological reactor, and an anaerobic digester, along with this red arrow sinks and transformation of energy through the facilities. So basically, the main source of energy is actually the wastewater itself. And in addition to that, we can have SSO or other carbon sources that Dru talked about. When thermodynamically, when we look at wastewater, it can have as high as 9.6 kilowatt hour per cubic meter energy within the wastewater. However, a big portion of it is not extractable. There are reports that up to 2.7 kilowatt hour per cubic meter can be extractable, and the number that I just compared with 2.4, 6, or 1 is way lower than this number, but still it's going to be very difficult in some cases to really go toward energy neutrality. The heart of energy neutrality, in my opinion, is the carbon diversion, that we basically divert the energy from the wastewater to the side stream, instead of going to the secondary, where we have to use a lot of energy from mechanical equipment and aeration. That itself has inefficiencies, energy loss, and there whatever that converts to CO2 is actually energy loss. On the other hand, whatever is really converted to biogas and using CHP and even THP, we can, as Dru mentioned, we can boost the amount of biogas. We're gonna increase the possibility of going toward the surplus energy that's shown in the energy side. In general, if these green arrows are bigger than the red arrows, obviously we are going more toward the energy neutrality. So in practice, there is no single recommended scenarios for a plant to be energy self-sufficient. However, there are ways to really look into it. One of them is the reducing energy consumption within the secondary treatment. I'll talk about it a little bit. Carbon diversion is a big part of it. Process intensification via advanced automation. There are 2 slides in the end that I like to tackle on this. Side stream treatment, it's a very, very important part of the energy neutrality. Dru talked a lot on that. Resource recovery itself, in order to reduce the load of secondary treatment, and obviously the mechanical equipment efficiency. No matter what we do, if we have a very very inefficient aeration system, probably is going to be very hard to go that way. Increasing the energy recovery from internal sources, how to boost the anaerobic digestibility by THP, and using CHP is a big part of the whole thing, thermal hydrolysis, and obviously other technologies that's pretty much emerging, such as pyrolysis that was mentioned earlier. And in addition to that, obviously the external carbon source will always add energy positive to a treatment plant. So we talk about the side stream. In order really to go over the practice we did here for Bonnybrook, I set an example that we did for one of the treatment plant in Maryland. That's WSSC in Maryland that we designed it, that comprised of THP, anaerobic digestion, equalization tank, and a struvite facility, and after that deammonification. And this arrows really shows that why we are doing these different technologies. It was talked about the THP digestibility, obviously for energy recovery, for solid rheology. One of the reasons that we use THP is actually to uniform and decrease the viscosity of the solids, and obviously the other one, through the lysis, we're going to have a lot of purge of nitrogen phosphorus that really boosts the energy, the phosphorus and nitrogen concentration and the resource recovery downstream. And after that, we're going to have struvite recovery. In this struvite recovery, I understand that Bonnybrook specifically study of Calgary is very interested in this technology. I listed a couple of different technologies that's used here: Fospac, Pearl, Magprex. These are the technology we use for comparative evaluation for WSSC, and which is for nutrient recovery, struvite mitigation, and of course load mitigation, and after that we use the deammonification. We're going to go through the similar practice here for Bonnybrook using simulation, a calibrated model on plant D and the side stream, to see the implementation of all this unit process, how in practice will help you to go toward the energy neutrality and conservation. So when we look at this process, if you have THP, anaerobic digester, and a dewaterability, obviously we will have a lot of struvite precipitation in anaerobic digestion and processes downstream of that, and because of the recirculation of a lot of phosphorus and nitrogen that is released through the anaerobic digester, and obviously THP will increase that concentration in the WSSC. I can tell you that ammonia concentration after anaerobic digestion was as high as 3,000 milligram per liter, so the dilution was a must in that case, and phosphorus was very high, approaching 1,000 milligram per liter, and you can imagine how that could potentially overload the secondary treatment. Then by implementation of a deammonification and struvite process on the centrate, what we can do is to a great degree reduce the recirculation of the nutrient load back to the head of the secondary treatment. We recover the nutrient as phosphorus in the form of struvite as phosphorus and nitrogen, and still in that case we have some struvite precipitation problem between the anaerobic digester and the struvite process. Because this struvite process is implemented on the centrate, we're going to have a higher quality pellet. The other technology that we evaluated is the struvite technology that is implemented on the digester sludge. Magprex or Aprex, the old name for it, was the technology we use. Obviously the pellet, the struvite you get is not as high quality as the struvite in the other technology. It has other benefit. One of them would be of course the mitigation of a struvite precipitation downstream of this unit, including the dewatering and the deammonification process. In this case, still we can mitigate and break the recirculation, a big amount of phosphorus and nitrogen going to the back of the plant. So in this practice, we're going to really go through how much that really is, how much this is really is going to really contribute to the energy conservation in your oil plant and the THP as well. When it comes to the technology itself, I talked about two technologies. I just want to, because of some interesting point on the dewaterability, I'm just going to, in the next two slides, go over it very quickly. This is a Pearl process. It's a Struvite process by Ostera. You are very familiar with this, and basically it's an inverse fluidized bed with different cross-sectional area. When you provide the adequate stoichiometry of magnesium, ammonium, phosphate, that's basically in the excess amount release. After the dewatering facility, you can precipitate struvite and remove it. And this is a very widely used technology, more than 20 worldwide installation. It comes in 3 different sizes, and with the phosphorus, which is sometimes to 90% phosphorus recovery, you will be able to recover 20% of nitrogen. There is other complementary technology that is based on the concept of an aerobic zone of a EBPR process, the release of orthophosphate when we provide an anaerobic zone on a VAS stream where we inject either fermentate that you have in excess in your plant, or even in some cases external carbon source. In that case, we're going to release more phosphate before the anaerobic digester, and that result in even more recovery of phosphorus and, as a result, nitrogen in the struvite process, which again further reduce the amount of nitrogen that is going to be to the head of the plant, and for that we spend a lot of energy. And the amount of this graph really shows the performance of the VAS strip based on the hydraulic retention time. It shows that close to the 8 hours, basically that is the adequate hydraulic retention time when we can maximize the release of phosphate and other cations, magnesium and potassium, in the VAS strip process before we implement a resource recovery facility such as MACPREX and Pearl that I talked about. MACPREX is another technology that comes on the digestive sludge. This is we actually installed designed and installed with the largest MACPREX facility in Denver, and that is on the digestive sludge. In addition to recovering struvite within the digestive sludge, another very important parameter on this is actually on the dewaterability of it. And we see that the blue section here shows that this process can significantly increase the performance of dewaterability that I'm going to talk about in the next slide. The reactor is going to be placed between the anaerobic digester and the dewaterability sludge. We are not injecting. We are not instead of really alkalinity, the way that they provide a higher pH values in order to really to fall into the KSP of precipitation of the struvite. They use aeration to strip CO2. When you strip CO2, obviously the pH goes up and the precipitation of the struvite happens. This is a graph that shows, this is a pilot study that was done in Miami on a MACPREX that shows that how the orthophosphate going into the MACPREX changed from around 200 milligram before the MACPREX to about 15-20 milligram in the effluent. But one thing that I want to really bring your attention to it is the amount of boost in the dewaterability performance of the dewatering after that upon the installation of MACPREX. And that's one of the benefits it brings compared to the Pearl process. The dewaterability is not a very well understood phenomenon. Centrate, that's a theory which contains orthophosphate, is reported to be correlated to poor dewaterability in anaerobic digested biosolid, and it's hypothesized that orthophosphate reacts with divalent cations and increases the monovalent to divalent, it's M to D ratio, and an increase in M to D ratio is shown to be really correlated with higher capillary suction time, CST, and as a result, worse the dewaterability. In your process, the process that I just went through can be implemented. I understand that THP is something that you guys have in thinking about and have pre-designed that's going to be on the VAS stream. You have 16 primary clarifiers, and you have 4 fermenters. The fermentate goes to the process, and the fermented sludge goes to a blending tank with the VAS and goes to digested CHP in the works. And after that, we want to see the implementation of this THP, this dewaterability, this Pearl process or MAC process, and MAC process and deammonification, how that really equates to the energy conservation in your process. We talk about the carbon diversion as a heart of the energy neutrality in a process, and that carbon diversion can be implemented by different means, biological means, physiochemical means. We evaluated 3 years of data from your plant, from Bonnybrook plant, to see how the primary clarifier is really performing in terms of carbon diversion, and this shows the TSS, BOD, total phosphorus at TKN removal via primary clarification, as shown here, that we have averaged 72% of TSS removal, which is incredible as a primary unit for carbon diversion. One thing that I want to draw your attention is, in some cases, even 20% of time, we are basically performing more than 80% TSS removal, which is incredible. That equates to around average 39% BOD removal, 23% TP removal, and 10% TKN removal. When we look at the process itself, we know that we have plant A, B, C, and D. There are some differences in the configuration. For this analysis, we use plant D, which is the most recent plant under design and commissioning, and we compare how much we can save energy for plant D if we implement these strategies. And the assumption was that whatever result we get, probably it's going to be a pessimistic comparatively result compared to A and B and C, where we can even save more energy. This table shows the influent characteristics and flow compared to the dewatered centrate and Shepherd Lagoon supernatant that goes to the head of the plant, as shown in the previous flow chart. We see that although just 1.8% of the overall flow is the recycled flow, but 12% of the entire solids going to the second treatment to the plant coming from the centrate and recycled flow in general and Shepherd. But if we look at the phosphorus and TKN, this number is actually very significant. Total phosphorus 52% and TKN 28% and ammonia 35%. That really shows how important it would be to really implement a proper side stream treatment to not only really recover the resources and leverage the energy production, but to decrease the load of nutrient going to the second treatment by a very meaningful degree. This is the model that we use. It's a calibrated BioWind model, steady state model we use. That's a plan D, and we basically assume if we implement all those changes in the side stream, how that really impact the effluent, the performance of the secondary treatment, the energy consumption in plant D, as well as the effluent quality, and we compare it with the existing data today. The first modeling we did was the impact of THP on the anaerobic digester. This is the anaerobic digester performance in the last few years. In Bonnybrook plant, we had around 53.8% VSR and TSS percent of 4.1% going to 3.3. The digested gas we got in the modeling was slightly different than the data, but we used it as a base model. We implemented THP, and I just want to draw your attention to some of this point. You see that, of course, the TSS percentile is going to go down in the effluent to 1.9%, but the VSS to TSS will changes from 60, almost 7% to 60%. The orthophosphate will increase significantly. The ammonia will increase significantly, and we're going to have around 20% increase in the biogas. In addition to benefit we get on the rheology of the biosolid, obviously we're going to boost the resource recovery potential and the biogas potential of the plant. This graph shows the comparison between 3 different scenarios, existing scenarios, where the recirculation is 34% of the total phosphorus going to the plant and TKN is 22%. When we have the side stream treatment, which is the deaminification and a struvite recovery, it shows that we reduce the orthophosphate recirculating back to the head of the plant by 80% and ammonia by 90%. That is basically decrease in the total load reduction of TKN by 15% and total phosphorus load reduction by 13%. If you implement THP in addition to the additional biogas we get, the most benefit on the nutrient we get would be on the ammonia, on the phosphorus side. We see that the total reduction even will increase from 13% to 22%. That is significant on the secondary treatment. This is the impact of side stream treatment on the load, as I said, in a graph site from 2,600 kilogram per day phosphorus going to the plant by implementing the side stream treatment, as well as the resource recovery. We can go to 2,200 and further down implementing THP to 20,000. The very same thing can happen. Can be observed on the nitrogen side. We see from 19,500 we go down to 16,700 on the secondary treatment. This is the simulated effluent quality on the total effluent, on the effluent TP, on the effluent total nitrogen, as well as the air flow requirements in Plant D and the digester biogas flow. I just want to mention that the 2.5 milligram phosphorus is basically with the assumption that we are not, at this point for the practice, we're not using any chemical precipitation. We see that by implementation of the side stream treatment, we can decrease this 2.5 milligram in the effluent in Plant D to as low as 0.8 and 0.6 based on the resource recovery and deaminification, as well as THP in the system. The effluent total nitrogen will have a significant improvement upon the implementation the side stream with decreasing the total nitrogen effluent from 17 to 11.9%. In terms of the aeration requirement, it shows that we went through 15% reduction in the aeration and 20% biogas production via the implementation of THP before the anaerobic digester. So basically, by implementing 15% reduction in the main, secondary, and 20% extra biogas, this is a significant step toward the energy conservation. But in a lot of cases, we do not really have the leverage of side stream in many cases, and in some cases, we have to take different approaches in order to really go toward the energy conservation. The main focus would be on the secondary treatment itself, and that is pretty much depends on the compliance limits that we are exposed to. This is the compliance limit for the Bonnybrook. It shows that when it comes especially to the ammonia, it's not as tight as a lot of places that we have to deal with total nitrogen effluent of 2-3 milligram per liter, total phosphorus of 0.1 milligram per liter. In this case, we can take other approaches. I really want to mention this. The relatively new approaches that's been showcased in a couple of full-scale plant, avian aeration technology, which is ammonia versus nitrate, to intensify a process by promoting SND through the secondary treatment. It shows that how basically, if I go through this very quickly, shows that when we have a very big aerobic zone, obviously the ammonia goes all the way to zero. When we increase the anoxic zone in a treatment plant, the nitrate goes lower, and there is a point that the combination of nitrate and ammonia is the lowest. That's exactly the point that we use for the advanced automation. We just nitrify it as much as is needed. When the ammonia is above NOx, we start nitrifying, aerating it, and when it's below NOx, we stop aerating it. That would be basically the type of DO you will have in the system instead of having a continuous DO. DO of 1.5 or 2 or whatever ammonia-based even control says. This is a kind of intermittent aeration. in one of the treatment plants that this strategy was implemented, they would be able to save 25% on the energy side without really compromising the effluent quality. That happened on the Florida. The temperature was higher, obviously. Every study, every case, every utility is different, and obviously it has to be tuned. But this is a very good technology in order to intensify the process to reduce the energy demand, and that could be implemented if or either with the side stream, or even in some cases that a lot of plants don't have the benefit of having the side stream as a means of energy management to be implemented in the secondary treatment. So in summary, implementing THP, AD, CHP, resource recovery and side stream deammonification process reduce the energy consumption by increasing the produced biogas and reducing the nutrient load to the mainstream by a great degree. THP itself added the biogas production by 20%, which is significant. And side stream deammonification is a very effective way of intensifying the treatment itself by reducing the nitrogen and phosphorus going back to the head of the plant. And for treatment plants lacking the side stream, still there are innovative approaches to move toward energy conservation, energy neutrality, and even in some cases energy positive plant. There is a plant, the largest plant actually in California, has a laboratory receiving solids, Hyperion, from different plants, but they can be easily energy positive. They have been energy positive for quite some time. Thank you very much for your attention.
All right, thanks. Thanks, Mehran. Thanks, Drew. Let's go ahead and jump into questions here. I apologize, we're running a little bit late, but that's all right. We'll keep going as long as people are willing to stick around. We've got some really good questions here. So I'll just start running through them. First one is for you, Drew. Question around what process is the centrate going to at the Green Bay plant?
Yeah, Green Bay has experimented with a few things. I have lost track, so I'm not entirely sure, but at one point, they may still be running this. They were running a WAS drip system. And I believe that the centrate was being combined with the downstream of the anaerobic. So in WAS drip, there's an anaerobic reactor on the WAS system itself to release the ortho-P. And I think the supernatant off of that is combined with the centrate and then goes through a struvite precipitation system. That was the plan. They really had ambitious goals of meeting 100% resource recovery through that program. And so I admire them for doing that. I just don't know if they had continued that program or not and what the status of it is, but that was essentially the plan. In the liquid stream process, I believe that they had capacity to manage the TKN coming back into the system.
Okay, comment on the Edmonton work. Basically, is Edmonton switching from cogen to RNG for beneficial gas use?
Edmonton is actually going to run both. They have a CHP system on site. The image I showed you included the CHP system that they have. Currently, the biogas that's produced from the dry anaerobic digestion process goes to a gas storage system, and then from that it goes to the CHP. I think they're running a couple of generators at about 800 kilowatts each there. So it's been quite successful on that front. They're interested on the new program will introduce significantly more separated source organics into the material recovery facility there, pre-process those, and then it'll go to a wet anaerobic digestion system there. The plan is to take the biogas, upgrade it to natural gas grade quality, and use it as a beneficial resource to the community. So they'll be, the short answer is they'll run both, is the plan.
All right. Kind of a general question here. In these processes, where does the final dewatering water end up? Is it being reintroduced into the process, or would that hinder the process if you do that?
Mehran, you want to take that one?
Yeah, you know, as I mentioned, that if you have the side stream, the dewatered scent rate really goes. If you have the resource recovery, it's going to go to resource recovery facility, it's per or and after that dehumidification and again going back to the head of the plant. And is that what the question is?
It's just specific to the
Yeah.
dewatering water.
Yeah, that's exactly what I showed in different flow diagram. That's how basically we deal with the dewatering center.
Okay, great, thank you. All right, this one's for Dru. Could you comment on the recovery value of biogas to CRNG given the fuel efficiency? How could utilities incorporate this in an analysis of options for biogas use?
Yeah, I guess short answer to that is you really need to dig into the local economics of those pros and cons. And I think you also need to, you know, the incentive programs, you really need to understand the how the CNG market, how the I think the EV market is important to understand. Our transportation folks have been very helpful to me in helping to kind of give our clients who are really, you know, their wheelhouse is the waste management side, and it's a stretch to get into the co-digestion piece. But then when we start talking about transportation and so forth, that's usually outside of that. So providing some consulting on, you know, what the transportation looks like, what the demand for what vehicles are going to be out on the road over the next 5, 10, 15, 20 years, and how that's going to affect demand, and how utilities want to really assess the risk of short-term versus long-term use of that biogas. The incentives, like I said, are very attractive, but they won't be around forever, and it's definitely an evolving market. So best thing to do is hire a competent consultant, work through the business case evaluation along with the environmental social criteria, really a robust analysis of those, do a comprehensive risk and uncertainty analysis on that, and then make a plan and execute. That's the best advice I can give you, but I wouldn't go into it lightly, and I would look at it, look at all those options very carefully over the short term and the long term.
Yeah, I think that's good advice. Very site specific, it seems.
Indeed.
All right. Let's see. Does advanced aeration control typically require investment to upgrade the control valves and aeration grid? And if so, do you have any examples?
Yes, in some cases it does, but in general is one of the actually cheap technologies in order to achieve what is achieved by implementing just some analyzers and probes. Analyzers and probes can be expensive themselves, and in some cases when we are dealing with very large plant, obviously the number of them are important. And one of the biggest challenges in that is the maintenance of it. With the current technologies, there is a tendency of drifting those values, and so the calibration program is a must in order to make sure that those parameters such as ammonia and NOx in the AVM process are accurate before we implement it on the basically the aeration control.
Okay, thanks. Back to you, Mehran. For the Bonnybrook study, did you run the analysis with phosphorus removal before or after dewatering?
No, in this case, we just, that's a good question. In that case, we just basically run the process based on the historical phosphorus and nitrogen removal on the Struwite technologies in general, what is reported. So there are some benefits that was not really included in the process, in the simulation process. One of them was how the dewaterability boost really impact the entire process. That may have some impact on the process as well, and that is not included. So in this case, it was just a Struwite recovery after the dewaterability, which is basically per process.
Okay, very good. Let's see, is there an example of a maximum load reduction achieved by side stream installations?
The biggest that I have ever seen is actually is around 27% in the nitrogen side, and that is one reason for it in the and that actually happened in the WSCC. One reason for it is there are in the WSCC area there were 6 plants, 3 of them are very large plant over 30 MGD, and all 6 plants send their sludge to Piscataway. As a result, the load of nitrogen was excessively high compared to influent, so they could even reach up to 30% of influent nitrogen load. But in general, it could go as high as 20% in the majority of cases, 18-20%.
All right, let's see, is deaminification the front-runner technology for side stream treatment?
Yes, deaminification, it basically is the name, a general name for all of them. As I mentioned, there are different technologies. I didn't really go over them for the sake of time. Here I can really, what we analyzed that was the comparison between Anitamox and Demon and Anamoc pack. These are the 3 main technologies with the most installation. There are 2 newer technologies called AMX and Xenamox. That's basically by Tomorrow Water and by Suez, very much based on the MABR technology. You may be familiar with it, but these are still on the pilot scale. We have 3 technologies at least with multiple full-scale installation, both in North America and around the world. All of them are called deaminification. In this case, what we did was the high-bass Anitamox process.
Very good. Let's see, without co-digestion, what's the maximum boost you can get in biogas with hydrolysis?
So without, go ahead, Drew.
Yeah, it's going to be really, again, site-specific, and it's going to be dependent on really the size and loading rate of the digester. So if the wet, it's hydrolyzing primary sludge isn't going to give you a much of a boost, but hydrolyzing the biological sludge or the waste activated sludge has shown to make that significantly more biodegradable in the anaerobic system downstream, especially, and this is an important differentiator, especially when the existing SRT in the system is 20 days or less. If you're running, so it's just important to understand the specific characteristics. So if you're running a very, very long SRT and, say 30 days plus, and you implement a pretreatment process like thermal hydrolysis, you're probably not going to see a big increase in VSR and also biogas production. Now, if you're running a short SRT and you implement THP, a short SRT being something maybe 20 days or less, you're going to see probably much more of a significant benefit from that. So, we typically plan on maybe a 20% bump in VSR in the WAS. So if it's a 50-50 loading rate on WAS primary sludge, then you might see an overall 10% benefit on the VSR and the biogas production. And that's typically what we plan on, is a modest increase in that. When you combine it with the other benefits is really where you start to see more bang for the buck on the handling cost downstream due to better dewaterability and better reuse options downstream.
All right, great. I'm gonna ask, we've got more questions here, but I'll have to follow up with everyone offline. If I didn't read it, I'm going to read one final question here and then we'll wrap it up. Do you have any real world experience on the impact of nutrient recovery technology in managing struvite in the solids centrate stream, such as before and after results?
Yeah, you know, one thing, yeah, basically, one of the very recent one that actually I was working on in the last few days is the Denver Metro, that they have a MacPrex and they are seeing phosphorus recovery up to it fluctuates. Obviously, we want to go toward 25% as much as possible, but right now it's not there. It's between 10 to 15%. We are in the optimization case, and based on that, obviously, when we achieve the 20% reduction on the phosphorus load, that would equate to the underloading of the secondary treatment. Yes.
Okay, great. Thanks, Mehran. With that, I'm going to go ahead and wrap it up here. Again, thanks to everybody that joined and those that stuck with us. We'll follow up with anyone that didn't get their question answered. Tony just put in the chat a link to Dru and Mehran's profiles on our website with their full contact information. You're welcome to follow up with them directly, and they'll be happy to help you with anything that you need. And we hope to see you on a future webinar, and have a good day.
Thank you. Thank you all.
Thank you.
Thanks.
Thank you.